We originally had this LabQuest set up here because the temperature in this room was so incredibly cold.
You needed a thermometer to know. Oh,
It was, in the summertime, it would be in the low 60s in here.
Yeah.
okay, so now we just need to figure it.
All right. So right now, the temperature is 21.3 degrees Celsius. Perhaps by the time we get the formula down, that might change. Oh, it's down 21.2. We'll see where it ends up.
21.1 now.
Now the formula, there are a couple of different formulas based upon certain assumptions here. And it unfortunately is not one that I memorize. I know where the formula is.
20.9 now. Go down to 20.8.
Now,
Yep, go
now-
down to 20.8.
is that number proportional, like say the temperature of the room, say 25 degrees Celsius, can you do proportions and find meters per second for that temperature, or is it
No, there's a square root in there.
square root in that?
So the formula I have here is, oh, actually, this does not have the formula in it. Does not have the square root. There are certain versions that do. Well, let's go with this one here. So the speed as a function of temperature is 331.3 plus 0.06. And let me double check that. Nope, off by a factor of 10. That's 0.606 times the temperature. Let's just double check against this right here. So if we do 331.3 plus
It says 20.7 degrees Celsius according to the probe.
Okay, yeah, well, we're just double checking that figure right there
Oh, okay.
to make sure our formula seems valid. So this becomes 331.3 plus 12.12, which is 343.42 meters per second.
Okay.
Okay, so.
If you ever put that on Google, must have just rounded down.
Yeah. And so, because there's some rounding involved in this, right, in that number. Actually, I think both those numbers have a little bit of rounding involved as well. All right, so at what point are we going to just call it down there?
Is it still at 20.8?
And it's
It's at
20.6 now.
Let's just call it at 20.6.
All right, we'll make it 20.6. Now, we're playing over subtleties here. This thing is not going to be that close, so, it's,
Yeah, because when you swing that, I think your body temperature will change around.
Maybe to the middle.
It's different measurement there.
we're going to pretend though. Plus 0.606 times 20.6.
I got a 343.78336, so.
All right. So somewhere around 330, 343, 344. I'm going to go with 344. You know what? 343.8. Let's go ahead and do it that far. So this becomes 343.8 divided by 2 times 0.799, and that is meters per second on top and meters on the bottom. So the frequency of the first harmonic is.
Um, 215 hertz. That's rounded. I don't know.
And for people like Holden and me, that's probably good enough, but you two have finer hearing. But let's take it 1 decimal place.
All right, that would be 0.1.
Yep.
So let's see what that sounds like. Two 215.1. Now let's swing it. Yeah, we nailed that. Now, if you can't hear it on the video camera, that's because there's something wrong with that speaker there. Now, the reason what's happening here is as I swing the tube, the air at the end of the tube is traveling faster than the air down here, because this is swinging through the air and it's moving air. When the air is moving faster, there's a drop in pressure, and so there's less pressure at this end than there is at this end, which is relatively still, and air will come up through the tube. As it comes up through the tube, it is ribbed, which causes the air to start to vibrate. You can get the same effect without the ridges in it. If you went into Home Depot, found a hollow plastic tube, like for insulation, whipped it around, you will hear a frequency. It's just not a nice note. It's more like a, or at a different length, it might be. But the pressure difference is not enough for us to hear that first harmonic. So the second harmonic actually is that's the second harmonic, and so let's make that prediction.
Second harmonic would be, that would be 1 wavelength.
Yep. We still have an antinode at the ends because we have the free ends.
But we do have a little, we have a wave, I don't know what you call that thing, that little hole thing in the middle.
This is antinode,
Oh, that,
where the sound wave is vibrating the most.
oh, okay, so we have an antinode.
Node, not node. Antinode at the ends also. 2 nodes.
Now, wouldn't it be the length is the wavelength?
Yes. So length is equal to the wavelength. And so same process as before. We end up with a frequency is equal to V over 2L. Over L. So we had a speed of 343.8 divided by 0.799. And we should end up somewhere around 430.2-ish. We'll get something more precise here.
Yeah, 430.3.
I knew it was going to be roughly twice that, because here we divided by 2, and there we didn't divide by 2, so that should be double that. So 430.5.
430.3.
Thank you. 430.3, just as is written. Thank you for the correction.
You're welcome.
All right.
No.
Pretty close.
They sound similar. Now there is a difference in the timbre because this is plastic and that's, an actual speaker. But let's see if we can hear the trill because we are close, or give some sense of how close we are. requires some coordination here, but. So I heard the trill, I think you heard the trill, Congo,
Yeah.
do you hear the?
Yeah, I know.
A little bit, okay.
Uh,
So it gives us some idea of how close we were. I suspect that we're probably about 10 hertz off, but from the point of view of 10 hertz out of 430, yay. Let's do the next harmonic. How many wavelengths is the next harmonic?
1.5?
What'd you say?
1.5?
You said,
2?
why 2?
I said 2.
Why? How'd you come upon 2? Just felt right?
No, I said 2, like 2 wavelengths.
Yeah, I'm probing you to find out why you said 2 wavelengths.
Oh, cause I just thought there would be, I just went with the pattern that there would be 2.
Ah, doubles every time?
Yeah.
Ah, okay. And Kong?
1.5.
Yeah. The pattern is not doubling every time, but adding a half every time.
Oh.
So it is indeed 1.5. So if we drew it,
Yeah, that's probably where that sounds like where I would have gotten that. Oh wait. Yeah, I think I realize it now.
so 1.5 wavelengths. And so what we end up with is the frequency is the speed over 1.5. Try that again. So therefore the wavelength is, that's 3 halves lambda, so this is 2/3 L. And so the frequency is 343.8 meters per second, divided by 2/3 of 0.799 meters.
Oh, 2/3. I gotta re-enter that because I put 1 point. I did.
Yeah, the 1.5 shows up here. I started to write it down wrong, corrected myself.
Oh.
So L is equal to 1.5 lambda, so lambda is L over 1.5 or 2/3 L.
Oh. Okay.
Oh,
Let
I see,
me,
I see now.
Let me fix that then, or try to fix it. 'Cause it's, okay, I got 645.4 hertz.
And that makes sense, because it actually is the sum of those two right there. Ooh, the units, nobody corrected me.
Hertz.
So the next harmonic should be around 645.4. And so let's play them at the same time to see if we get the trill. It will get worse and worse as we go. However, if you wish hard enough.
Yeah, I could kind of hear it.
I heard it, but it seemed like the tube was
Yeah, the tube.
canceling out the speaker. Like all I was
Yeah,
hearing
the
was
tube
the tube.
sounded deeper as well.
Oh.
Or-
Oh, as in if drowning out this that?
Yeah.
But then the
You can
tube-
fix that. Much to the delight of everyone on the hallway.
Hmm. Oh, okay, I hear it now.
Yeah, I could hear it.
Oh, definitely hearing that.
Yeah, I definitely hear it.
Now notice that when I'm spinning it, I'm spinning it around like this. Because if I spin it around like this, Do you hear a trill there?
Yeah. I can hear it.
We got a Doppler effect going on in that case, which I don't hear since I'm at the center of it, but if I'm doing around this way, we're eliminating the Doppler effect as much as we can. But because the tube is coming towards you at some part and going away from you at other parts, there should be a changing in the frequency as it spins around.
And then your distance away from you would also impact as well? Is that the point of Doppler effect? Is also
Doppler effect
how far away you are?
Not necessarily how far away you are, but how fast the thing is going towards you or away from you.
Oh, I got you.
Yeah, you know, in those in movies where you'll hear the car go, you'll hear the beep and then it goes,
Yep.
with cars, truck horns and stuff like that. That's the Doppler effect.
Even the Prius, except that's more of a.
Yeah. But yeah, that's pretty much the Doppler effect in action.
All right. We can go one more frequency. Let's go ahead and do it since we can. So that was the third harmonic. We're about to do the fourth harmonic. Fifth harmonic is so hard to get off the tube that we'll just stop at the fourth. So how many wavelengths?
2.
There's the 2.
And so the wavelength is half the length of the tube. And so my frequency should be 343.8 meters per second divided by 1/2 of 0.799 meters. And somewhere around 860.6. And drawing it. Something like that. Or is that the one I just did? It is the one I just did. So it's nothing like that. There we go.
So, am I doing it right? Just want to make sure.
Divided by. Yeah, that'll do it.
Okay.
It looks like you're drawing DNA.
Yeah. The
860.6 hertz.
what's it? Okay.
Oh, you already wrote it down. Yeah, you already wrote the answer down. I was telling you the answer.
Yeah, I was doing it based upon doubling this, but rounding could throw it off. Because that 1/10 of a hertz, we would notice. They would notice. We won't. They would notice. Yeah, this one always looks like sort of a wrapped candy. And then at some point you do get to the DNA. Oh, how many times have I knocked that over? All right. So, second, third, fourth. That's the fourth harmonic.
Sounds like it also sounds like the faster you spin it, you get there's an increase in volume as well. Because of
Dave.
this, it feels like it also gets louder.
It's positive higher frequency. You can feel the
Yeah.
difference higher frequency, but the same amplitude.
Now,
I was thinking that it was also because it was spinning faster and air was rushing through it
the
faster.
pitch gets higher.
Or is it there's certain frequencies that we just hear naturally louder, that our brains are designed? Because I know with light, there's certain frequencies of light that we see much better than other frequencies.
Now that you point that out, that makes a lot more sense.
But I don't know. It's also possible that, because I am swinging it faster, but that fifth harmonic, I think starts dropping down. So it's second, third, fourth.
Yeah, it is dropping. Yeah, I wonder why the fifth is dropping down like that.
Also getting more of a rush of air at that point. It's like the sound gets diluted. That's sort of the way my brain is thinking of it. All right, so 860. I don't know if you can.
I can hear that.
Yeah.
All right,
Yeah,
I'm gonna
we're-
crank this up, just to, again, for the delight of everyone around us.
It seems like there's a, what'd you call them, it starts with a T.
Trill?
Trill, it seems like the higher the frequency we go, that trill's more apparent, like it's not, we can't hear it as many, or it's not, I'm trying to think of how to describe this, like,
So there's fewer trills per second?
yeah, fewer trills per second, yeah.
Which would imply that we're actually, our predictions are getting closer to
Yeah.
matching than before,
Mhm.
which seems odd. Because typically when I do it, it seems like we get farther and farther off, but what's the magic of the groove? So I'm hoping this gives some credibility to the stuff that we're talking about, the fact that with a simple child's toy, we can make predictions and get close enough. Now let's take it to the next step. Questions to hear?
I don't have any.
All right, why don't we take a small little break while I set for the next part? I will actually pause this and hopefully remember to start it back up again.
I'll remind you.
Thank you, I would appreciate that.
You're welcome.
Yep.
Yeah,
I think it's recording. Well, someone gets to see the color of my shirt right now.
I
Yep.
think
Yeah,
it-
it's recording,
it
I see a
took
red
people-
light blinking.
I think it took people like Einstein to start making explanations to truly understand light. Or is it, yeah, it took people like Einstein to,
Yeah, I mean, they're basically 20th century physics trying to deal with that. All right, so we have basically, it's a water tube or a sound tube, depends on how we want to use it. I pour water into the reservoir here. Now, the height of the water in the tube and in the rubber tube and the height of the water here should be the same. So that's based upon the shadow that I can see, and I don't know if you can see it. I'd be shocked if you can, but
yeah, I can't see it. I have to get
But
closer.
it's roughly the same, that's what.
yeah. Although, oh, actually. I will say roughly the same because this one actually seems a little bit higher. No, it dropped down. There we go, okay. Apparently there's an air pocket. So the water in the tube, this tube right here, comes about here and here. So we can change the height of this just by changing this. Apologize for the screeching. So by lowering that, we can lower the amount of water in the tube here, and that water will just start filling into the reservoir. Because basically, it's going to do it, assuming that there's no kinks in the line, or basically garbage in the line, which apparently there is. It will do it till the air pressure basically is the same on both sides, or you reach equilibrium on both sides, based on the air pressure. And so I can also put water in there, or I can raise this. And hopefully you can see the water level rising here.
Yeah, I can see that.
And there's a lot of stuff in there. Fortunately, get that lovely metal on metal sound. All right. Then I take a tuning fork. Sounds like about 320 hertz.
Sure.
Yeah.
Yeah, I wouldn't know.
Now there are a couple ways of finding this. One, it's printed on here 320, so that's the way I usually do it. But if you're feeling more industrious, we could get the microphone, record the sound coming off the microphone or the change in pressure coming off the tuning fork in the microphone, and then do a plot, do a curve fit. And matter of fact, let's go ahead and do that. We have the technology, and we have the time. Oh, that's magnetic field sensor. There we go, microphone. So we don't need a temperature probe anymore. Now it has sound pressure right here, and you see it's on that. And if I bring it up here, notice that we can change the pressure, or we have an ambient number there. Again, I'm assuming all of you have better eyesight than I would have, and you can see that number.
You think
Yeah, I
the
can
mask
see.
is keeping the pressure, like,
Oh.
holding like pressure back, like kind of affecting its flow?
Oh! There was a drop there. All right, so let's look at a graphing screen, because that might actually show. Oh, that thing's not gonna run very long. Oh, it helps if I actually hit the right button there. Oh.
There we go.
Yep. And you can see I'm not singing a perfect note there because it's all jaggedy. Let's do the tuning fork.
You want someone to hold it?
I'm gonna be arrogant for a moment and think I can do it by myself, but when it fails miserably, help would be appreciated.
Okay.
Oh, that was not what I was expecting there. So we do have somewhat of a pattern there, but let's see if we can actually do that better. Roland, I would appreciate the help. I can let you do tuning fork, and don't do it that way. Okay, just one ping. Let's see if we can do better than that. Hold on. 10,000 samples a second. Let's see if we can up that. Whoa, didn't mean to go that far. Adjust invalid entry. All right. Okay. Thing when ready.
Is it because I was on too?
All right, let's try this. Try to hit rubber on metal instead of metal on metal. Okay. Now? Yeah. Whoa, there we go.
Sweet.
Yeah. Yeah, if you,
Yeah, I can hear you.
Get out of here.
All right, so we have a nice curve finally. All right, thank you, Holden. And so we can curve fit with these things. Yeah, I guess you haven't done any curve fitting in this class. You did some in 131?
I have not done any of that at
I
all.
don't recall doing perfect.
Alright, so you're gonna analyze curve fit, cover the way they labeled it, then you check the one thing that there was an option for. And we can either do a sine or a cosine, it doesn't really matter which one we pick for this. So I'll just do cosine. And what it's telling us here whenever you do a curve fit, always, what's gonna happen is you've got the, in this case, red, the red line which matches what was being measured, and then there's a black line put over top of it when you do the curve fit. Now sometimes, for whatever reason, it comes up with some really bizarre fit for the data. And it's very clearly the black line does not match the data that you're trying to map. So just generally if something like that happens, you choose a different sample size. You know, that one we did the whole thing, but you know, choose this much or that much or somehow so that it's not getting confused by how much data there is. But the curve it is mapping is y is equal to 0.043679 cosine 2008.2 plus 70154 plus 2.5166. So this is the equation that it's giving us. And just so it's giving pressure, but I'm trying to think of what the units are for the pressure there. And it's not really giving it to us. I would guess pascals, but I'm not 100% sure. All right, so that's the amplitude, because as this thing is vibrating back and forth, there's some mean value right there, that's this number right here. And then that's the amplitude, that's from the mean to the general peak or to the valley. Oop, I lost my time. There's a time there. What is the number in front of t, and what is this number here?
And then 2000